Hello guys, today in this video I'm gonna make you learn how to prove the De Morgan law on proteus by using the AND OR gates. So these are the two equations for the De Morgan law. It states that the sum of the two input values and by taking its inverse will be equal to the product of the opposite values. Similarly, if we take the product and then take its inverse, then this will be equal to the x inverse plus y inverse. Here the plus sign indicates that it is an OR gate, and the dot sign, which is generally the multiplication sign, indicates that it is an AND gate. So here you can see that its output is x plus y dash, because dash is the complement sign which is indicating that the NOT gate is attached at the output terminal of this OR gate, and here are the two inputs x and y. These are the two inputs x and y, so this should be equal. So first let's come towards this table. You can see that 0 and 0 will be equal to 1. So let's see here, both the inputs are 0 and it is equals to 1. So if I take the right hand side of this circuit, then this 0 will be always equal to 1, and in all the situations the LED will be turned off. It means that it is showing the 0 logic state. So here you can see that if I turn on the logic toggle, then you can see that all the LEDs will be off. Then here you can see that here is going on. So this De Morgan law statement is proved. So let's come towards the second equation of the De Morgan law, which is implying that I have just only copied and pasted the circuit here and reversed the gates. So this is the equation for De Morgan law. So here you can see that this is the table for this De Morgan law. Actually, the fourth logic state, there is an issue in copy and pasting it, so the fourth logic state is not appearing. So I'm gonna make you learn how does this work. If the logic states are 0 0, then it will be 1. If the 0 1, then it will be 1, and if 1 0, then it will be 1 2. It will become 0 only in the situation when both the x and y terminals are at the one logic state. So let's see how it's work. So here you can see that both these circuits are giving the equivalent outputs when you have the logic states x and y is equals to 1. So generally you can see that x dot y means 1 into 1 is equals to 1, and its complement is 0. So here the 1 complement is 0 and the y's complement is also 0. So 0 plus 0 0. So these both states will be at 0. So if I change the logic state from 1 1 to any one, so here you can see that all the LEDs will be turned on in all the situations when you get one input on or the other off, and both the inputs off. So here is a simple example for this function. You can see that this function, I'm just showing this function for the simplicity and how to implement these functions. It is generally showing x and y. So x and z are in multiplication, so the multiplicand is the AND gate, and the addition which is generally done by the OR gate. So y and z will be in this terminal, and the third terminal is x that is connected to the OR gate. So the LED is showing the output values. So if you see that if 0 0 0, then it will be 0. So let's take a simple example for this. 1 0 0, it will be 1. So here is 1 0 0. Sorry, x is 1. So x is 1 and both the y and z are 0, then it will be 1. So if the both are 1, you can see that the F is 1. So if 1 0 1, so you can see that the LED will turn on. It is showing that the 1 logic state. Similar functions are appearing here, which has the 4 inputs but 1 function. So 4 is equals to 2 raised to power 4, and that is equals to 16. So there will be the 16 logic states. So A, B and C and D, 0 1 0 1 0 1, and repeating this. So here is 0 0 and 1 1, 0 0 and 1 1. Here is tetra 0 and tetra 1, and then it comes the 8 values are 0 and 8 are 1. So let's compare the graph with the following logic outputs. If we see that, let's take a general example. Here is 1 0 1 1. So I will let you know how does it work. So this is the function. So if the logic state will be at 1 0 1 1, so the circuit will be off. So 1 0 1 1 is showing that here is 1 0 1 1. So the logic state 0 is appearing. So if it is at 1 1 0 1, so the LED will get turned on and is showing the 1 logic state. So come towards the other example for this graph, 0 0 0 1. So 0 0 and 0 1, then it will be turned on. So the fourth function here is this. You have to make the graph by your own self, sorry, the logic table by your own self, and let me know in the comment section what have you learned from the previous graph, previous truth table. So here you can see that it is working like this, and this is the function that I have implemented because you can see that all are in complement form. So if I apply 0 0 0 0, then it will be 1 1 and 1 and 1. So you can see that 1 into 1 is equals to 1, 1 into 1 is equals to 1. So after the addition, you can see that the 1 plus 1 is equals to 1, so 1 is appearing here. The second, if I apply 0 1 1 1 1, so you can see that there is 1 and there is 0, here is 1 and here is 0. So its complement will be 0 1 and 0 1. So you can see that 1 will be multiplied by the 0 and here will be multiplied by the 0. So 0 plus 0 is equals to 0 though. So the 0 output state, logic state, is appearing here. So I hope that you have learned much from this video. If you really like this video and enjoy this video, please don't forget to subscribe, share and like my channel as well. Thank you.